In this video we're going to be talking about rotations making use of a coordinate system. And we're going to start by looking at rotations centered at the origin. So if we think about this just a minute, when we're looking at transformations of different types, it depends on what coordinate system we use, which one is easier or harder. So for example, when we're working with parametric or rectangular coordinate system, it was very easy to do translations. Okay, so for example, when we had x as a function of t and y as a function of t, if we wanted to translate by the vector, say AB, then our new x is just our old x of t plus a, and our new y is our old y of t plus b. So, for example, if x of x was originally given as t squared, and y was given as cosine of t, and we wanted to translate by the vector 2, 3, then our new relation, so this is the old relation there, the new one would just become x is t squared plus 2, and y is cosine of t plus 3. So very easy to do. When we wanted to switch this to equations, let's say you have y equals x squared and you want to translate by the vector AB, remember we had to sort of put the inverse function into it, inverse relationship. So if we want to translate by b, we had to replace y by y minus b, and x, translate by a here, by x minus a. So if this is 2, 4, for example, this would be y minus 4 equals x minus 2 squared. Of course, you could solve for y or solve for x, possibly, depending on the type of equation. But the point I want to make is mainly that it's pretty easy to do translations when you're in rectangular coordinates. Well, it's also very easy to do rotations, at least about the origin, if you're in polar coordinates. Remember, in polar coordinates we give, rectangular coordinates, we give a point here, say 2, 1, as a distance horizontally and a distance vertically. We can also locate points, like this might be 2 square root of 2, and then this might be an angle of pi over 4. This is given as a radius r, distance from the origin r, and a rotation angle theta. So we give these ordered pairs as r thetas. And so we'll typically give r as a function of theta. Now, if we're having that situation, it's very easy to rotate a point, because if you have it here and you're rotating about the center, and say this is the angle theta, we can just rotate an additional angle phi or phi, whichever way you want to pronounce that, by just the point stays at the same distance from the origin, so the r stays the same, but the phi is just added to the theta. So the new angle from here is theta plus phi. Okay. Now, of course, as with the rectangular ones, when we're given r as a function of theta, we have to do the inverse operation when we're working this in. So that's basically what this is talking about here. So it's very easy to do that. So the new r prime is the old r, and the new theta prime is the old theta plus phi, or phi. Okay, now remember we have the basic relationship that x equals r cosine theta and y equals r sine theta is our basic connection between the rectangular and polar coordinates. So if we want to see what happens in rectangular coordinates with translations like transformations, we can apply this. Let's take a look here at an example, though, before we do that. I'm going to pull up this program Graphmatica, And I'm going to actually go to options and change to a polar grid because that's what I'm going to focus on. And let's graph something. Let's say r equals, let's say 8 cosine of 5t. So we get a nice little, what we call a 5-leaf rose curve. Okay? Now, what if I were to take the t and replace it by t plus pi over 6, let's say. Okay, how about t minus pi over 6? Let's do that. Okay. So what we should see here, look what happens. We have exactly the same curve rotated by pi over 6 in the positive direction. So the point that was here for the pre-image, its image is right here. So it was at r of 8 and theta of 0, or t or theta of 0, and this gives us an r of 8 still, but a t of pi over 6. So everything is the whole thing's just been rotated. Of course, if we'd done it with plus pi over 6, we would end up rotating in the negative direction. Okay? And so you can see this leaf right here has now been rotated down here in the fourth quadrant. So there's a good example of what's happening here. Very easy to see what's going on in polar coordinates. Okay. Now what happens in rectangular coordinates? We're going to make use of this. So what we're going to do is we're going to take a relationship, a point xy, write it in polar coordinates, rotate it, and then switch it back to x and y. Okay. So here we go. X prime is going to be r, the old x, it's going to be the new r cosine of the new theta prime. Okay, it's the new r prime, which is the old r, and the new theta prime, which is theta, the old theta, plus our phi here. Now, we're going to use an identity. This is an important identity from trigonometry, and you can see a proof of this in my trigonometry ultimate sketch. But cosine of theta plus phi is cosine theta cosine phi minus sine theta sine phi. We're going to distribute the r, and so we get r cosine theta times cosine phi, r sine theta times sine of phi. And also, notice that I've also grouped this. So I've used the distributive property there and some associativity. Now, the r cosine theta is our old x, and the r sine theta is our old y. So the new x prime is our old x times cosine of phi minus the old y times sine of phi. So quite a bit more complicated than just translations in x and y coordinates, because for translation horizontally, we just replace the x by x minus how much we're going to translate horizontally. This involves the x and y and the angle and a couple of trig functions. In a similar manner, let's look what happens with y. Well, the new y prime is the new r primes of the sine of the new theta prime. Again, the new r prime is the same as the old r. The new theta prime is theta plus the old theta plus phi. Now, we also use another trig identity. Sine of theta plus phi is cosine theta sine phi plus sine theta cosine phi. Distribute the r cosine theta sine phi plus r sine theta cosine phi, and again, notice that we get an old x and an old y out of this. So here is the basic setup. So if I know my old coordinates x and y of a point, and I want to find my new coordinate x prime y prime, then I can just plug in these formulas here. So this is what you actually do to the points in the table. Okay, so let's take a look at an example here. So let me go back to Graphmatica and just clear out everything. Actually, let's just delete these. And let me go in and let's put the paper back in regular rectangular paper, coordinate system, coordinate background. Okay, and let's just start with something easy like y equals x squared. A nice parabola there. Okay, and let's take a point on there. Let's say 2, 4. So there's a table of a bunch of values. Here's one of them, 2, 4. So suppose we take that point there and we want to rotate that specific point. And suppose we're going to rotate it by pi over 3 in a clockwise manner. Counterclockwise, positive manner. So, well, it should stay the same distance away. What is that distance, by the way? Let's see. If we're talking about the point 2, 4, the r there, this is, of course, this is xy. The r is the square root of 2 square plus 4 square. That's 4 plus 16 is 20. Square root of 20. 20 is 2 squared times 5. 4 times 5. So that's 2 square root of 5. Or square root of 20. Okay? So if we did a circle, watch this. If I do a circle centered at the origin of radius square root of 20, it would be x squared plus y squared equals 20. R squared, which is 20. And so if I did that, or just do r, I can do it in polar here. R equals square root of 20. So we know that the image is going to be, should be on that circle somewhere. And it should be rotated by pi over 3. Okay? Is where we want it to be. So we will rotate by pi over 3. Okay? So let's go back to here. So here is what we need. Now we need to get this formula. Let's see, where's our formula? Okay, here's our formula right here. And we need to plug in pi over 3 for theta, or for phi, excuse me. Okay, so we're looking at it up here. We need cosine of phi and sine of phi. So cosine of pi over 3 and sine of pi over 3. Let's take a look at that and remember something about this here. These are some things that we typically use a lot. Pi over 3 can come exactly from an equilateral triangle. And if we'll split that right here with the right angle there, then this little angle is pi over 6, 30 degrees, 60 degrees. And if this side is length 2, then this side is length 2, this side is length 2, this side is length 1, and we'll call this guy, A or something. So we know a squared plus 1 squared equals 2 squared. So a squared plus 1 equals 4. A squared equals 3. A is, well, plus or minus the square root of 3, but A is a length. So A is the square root of 3. So that's the square root of 3. So let me redraw this. So if you're looking at, if this is pi over 3, this is 1, this is 2, this is square root of 3. Not exactly drawn to scale, but we can now find the sine, cosine, and tangent and so forth of this. So the cosine of pi over 3 then is adjacent over hypotenuse. It's 1/2, and the sine of pi over 3 then is opposite over hypotenuse, square root of 3 over 2, and that's what I have here. And so now we can use those values and plug those in the formula. So here we have cosine of phi. Cosine of phi is 1/2. So we get 1/2 x and here we get minus, because of this minus here, square root of 3 over 2 times y. And so that gives us x prime equals 1/2 x minus square root of 3 over 2y. Now, to get y prime, we plug in, again, the same numbers here, square root of 3 over 2 times x plus 1/2 times y. Now, we can now apply this to as many points as we want. Let's say we do it to the one we were looking at here, which is 2, 4. Okay? And we just plug that in for x and y in this formula here. So if x is 2, 1/2 times 2 is 1. So that's the 1 right there. And then y is 4. The 4 and the 2 cancel, leaves us a 2 times negative square root of 3 is negative 2 square root of 3. So this gives us the point x prime, the image of 2, 4. The x-coordinate will be 1 minus 2 square root of 3, approximately negative 2.464. Okay? So 1 minus 2 square root of 3. Okay, how about the new y prime? Its image, we plug in, again, 2 and 4. So this time we put 4 goes in for x here. 4 divided by 2 is 2, times this is 2 square root of 3. I'm sorry, this is x, it's 2, excuse me. The 2's cancel and you just get square root of 3. The 4 goes here, no for y, and half of 4 is 2. So it's 2 plus the square root of 3. So let me graph that here, and let's see if I can put that number in here. X is 1 minus 2 square root of 3. And y is 2 plus square root 3. Okay, and notice now that it did stay on the circle. That's a good thing. And we should see the angle from here to the center to here should be 1/3 of pi. If you look, at least it looks reasonable. Okay, so now what if I wanted to do this over and over and over again? Well, here it is for a whole bunch of points, and I could graph all of these points, and this would start to, and of course I'm lining them up pre-image to image like this. Of course the fixed point is the origin, because that's the center of our rotation. That doesn't change. And we could continue doing this and get a graph, and that's essentially what we're going to do. Now to do this in Graphmatica, then what I want to be able to do is actually come up with a formula. Now remember, when you put it in, when you're going to the formulas, you have to basically use the inverse function. Well, the inverse function of rotation is a rotation about the same center going the other direction, the opposite direction. So basically we can use these formulas here and put in minus phi in place of phi, and this will tell us how we have to change x. Now remember, cosine is an even function, so cosine of minus phi is the same as cosine of phi. Sine is an odd function, so sine of minus phi is minus sine phi, so that makes this a plus here. And again, this one's a minus, and this one stays plus. So these are your basic formulas here for what you do to x in the formula. Okay, so let's see if we can do that to our y equals x squared formula. Okay, so y equals x squared was our original. What's our new relation that's going to graph the rotated parabola? Okay, so we replace the y with minus x sine of phi plus y cosine of phi, and we replace x with x cosine phi plus y sine of phi. Of course the square's on the outside. And if we plug in our pi over 3, which is our specific phi, and put in our values that we know, sine of pi over 3 and cosine of pi over 3, what they are from above, it boils down to this right here. So I should be able to type this in Graphmatica. Let's see if I can graph that in. Look, one thing that's nice about Graphmatica is I don't have to solve for y. So minus square root of 3 divided by 2 times x plus 1/2 times y. You know what? I don't think I need this, but I'm gonna put this parentheses in here. Okay, and that's supposed to equal this. I do need parentheses, and then 1/2 times x plus square root of 3 divided by 2 times y, close parentheses, power 2. Okay, hopefully that does it. Let's see what happens here. Okay, when I graph this. Notice it does take this point here to this point right here, and it takes the entire parabola and just rotates it. And it rotates it by an angle of pi over 3. Isn't that cool? So this is how you can rotate graphs. Okay, and so you can see that. Now, this is rotating what? About the origin. Now, how are we going to do it if we don't rotate about the origin, but we rotate about, some other point? Well, this is where we can really take advantage of transformations and the fact that we can compose them. So what we want to do, if we want to take a rotation, say about an angle phi, about an arbitrary point AB, we can first translate the figure by the vector minus A minus B, which basically takes the point AB and sends it to the origin. Rotate about the origin, as we just did, and then translate back by the vector AB, and that's going to turn out to give us what we need. Okay? Now, if we can represent R sub theta, or SAR sub phi, as a rotation about the origin through an angle phi, and T sub vector AB as a translation by vector AB, then we can think of this as T translate AB, compose, rotate phi, translate minus A minus B. And of course, translate minus A minus B is the inverse of translate AB. So the products of this type are called conjugation. And what we have here is we're using this is what's called left-handed notation, which is you start with your points on the right and you work your way back from right to left. So you start with your point on the right, first apply the translation by minus A minus B, then rotate by phi about the origin, then translate back by AB. So they're backwards from the way we read. Now, this is the way that they're typically done in composition of functions in your algebra classes, or your beginning algebra classes, college algebra classes, and pre-calculus, trigonometry, calculus, and so forth. And a lot of times you'll see this even in your linear algebra books. So I'm going to use this notation. I actually personally prefer writing this backwards, so that we start with the transformation on the left, and work our way left to right. This is the way group theorists do it. Okay, and so that's what we have there. So now we can we can do any of these rotations by doing these compositions. Now it's going to be easier to figure out what happens with the formulas in these once we represent these things as matrices. Then we can just take the matrix that represents each of these translations and this rotation and multiply them together, and we'll get the matrix that makes the general rotation. And we'll look at that a little bit later on down the line. Well, actually, let me see. I can probably take you right. Well, we'll do it later when we talk about the matrix versions.